So, this component right here, this happens to be a coal-fired power plant. But the turbine and the generator, the turbine and the generator can be found when you burn coal, petroleum, natural gas. Those are our typical fossil fuels. But also if you burn biomass, or with hydroelectric. In hydroelectric, essentially, instead of having steam turn a bunch of blades, the wind turns the blades. It's the same thing. Nuclear. We'll find this same thing in a nuclear power plant, except we use a fission reaction to make the steam rather than a combustion reaction. Geothermal. So you can see that this little combination of things right here is a very useful combination. And essentially, except for photovoltaics, where you're actually using sunlight to generate, cause electrons to move from one substance to another, which is essentially an electric current. Aside from that, the vast majority of our electricity generation comes from this little combination of factors. And remember when we were talking about energy types, that when we do transduction, that if you rotate a coil of wire in a magnetic field, it generates an electric current. Okay, I don't know how many of you ever did this when you were little kids, but you take a coil of wire and you wrap it around a nail. Anybody remember doing that, like in elementary school? And then the wire connects to a light bulb, and you basically take that little nail with the wire and you move it through a magnetic around a magnet, and the light goes on. That's basically that. So that's kind of a central sort of concept you should know. That's how we generate electricity. Move a coil of wire through a magnetic field. Okay, and then I think I also said that prior to responding to the Clean Air Act, these three parts basically weren't there. This isn't central to making electricity. These three things are what remove pollutants from the exhaust. Basically, you're burning something and you've got an exhaust, just like you have in a car or at a campfire. And the exhaust typically goes out there. And these three things remove various different pollutants from that exhaust stream. Most of the footprint of the power plant is those things. So we'll talk about that a little bit more. Okay, so let's see. I'm going to be able to see that real well. I mean, you go to a power plant and you get nuts that get screwed onto bolts. I'm not kidding, that are this big. So the wrench that they use I don't know how the guys do that, if they like 4 guys jumping up and down on a wrench, to turn that nut. But it's all huge industrial scale. I don't know who makes those nuts. I mean, it would be, just these gigantic things. Everything is huge scale. Basically, from the coal pile, like we said, the Marshall Steam Plant has a 42-day supply of coal. The coal comes down through here. There's an initial crushing process, and then it gets ground down to a fine powder and gets dried further on down the process here. And this is actually at the bottom of those chutes. You get these. It's like a mortar and pestle. Have you seen those things? In where you grind up things. That's basically this is the pestle here, and it's grinding up that coal, and it gets dinged up. Eventually, those things have to get replaced. But it gets pulverized down here, and then, like I said, it's the consistency of talcum powder. And that's to make sure that as much fuel, that's the coal, gets exposed to oxygen as possible. If you burn a chunk of coal in your fireplace, that's a lot of volume inside that chunk that's not exposed to oxygen. And remember, you got to go back to your equation for combustion. You need fuel and you need oxygen in order to produce the thermal reaction. Okay, so that's what burning is. And so we want to maximize the efficiency of that process, and that's why it's pulverized down to the consistency of talcum powder. So here's kind of what it looks like. It's kind of dark. You can see it on my screen. You can't see it on there real well. But it's neat. We walk by, you can actually grab some coal before it's actually pulverized. That's kind of what it looks like. I took that with my smartphone, so it's a little blurry. I don't really need to see that. So this is the door to the furnace. The furnace is huge, so it's 7 stories high. One furnace. So one furnace, there are 4 boilers, 4 furnaces at Marshall Steam Plant. The water runs through these tiny little tubes inside of the wall of the furnace, and it gets heated to 3,600 degrees. And in the process, that gets turned into steam. What falls off the bottom? This is a former student who did. By the way, if any of you guys want to do this, how many of you still need a lab-based science class? You guys all have a lab-based. You could take ENV 120, which is basically a lab-based version of this class. And then we go to these neat places. It's really a lot of fun. Oops, going the wrong way. So at the bottom of this thing, 2 things happen here. When you burn that dust, and there are large chunks that basically fall out at the bottom here. Okay, that's called bottom ash. And then there is fine particulate matter that comes out through the top, and that's called fly ash. So bottom ash, fly ash. Okay, and those they call them. When you work in the industry, people come up with names for things that might not be found in the textbooks. So if you go to Marshall Steam, they call the bottom ash, they call them clinkers. You won't find that on a test, but it's kind of cool. You get the guys in there, yeah, those are clinkers. Get rid of the clinkers. So here's what the turbine looks like. That's a turbine. All right, so it looks like a jet engine with all these blades on it, and that is what the steam is focused on. And when that 3,600 degree Fahrenheit steam blows on that, it gets that thing spinning, okay, and it spins along that axle right there, and that's the axle that turns the coil of wire within the magnetic field. So this is that unit actually in the Marshall Steam Plant. So here's the steam coming through this series of ducts, and it gets blown onto the turbines, which sit inside these structures. And one of them is a turbine, and the other is a generator, and they're connected by the axle. So the turbines are in here, and these are the magnets, and as that thing spins in there, that's where our electricity comes from. And this is what the place looks like. Obviously, you have to do something with that electricity, and it gets taken away with these high-tension wires. So the Marshall Steam Plant, right there on Route 150, it's a 2,000 megawatt unit. So that's the rate at which it produces electricity. Just so you know, Duke Energy in the United States produces almost 20,000 megawatts, and that capacity is broken up from 3 nuclear power plants, 8 coal plants, 31 hydroelectric plants. So, you know, every one of the dams that dams up the Catawba River, there's a, I don't know if they all have them, but they all have the potential of having a little hydro. And in a hydroelectric plant, basically you just have a turbine that's turned by the water falling through the dam, and that turbine then turns the generator and makes the electricity. So it's the same principle. And then a couple of other combustion turbines over there. But that's basically how we make electricity. Now, let's talk about all these things. Okay. There's a lot, you know, just like when you, how many of you like making campfires or sitting by the campfire? Okay, you know, sometimes you sit around the campfire and the wind blows a certain way, and that smoke gets in you and you're, bleh, okay. Well, that's the same thing happens when you burn coal. That's what normally would come out of the stack. So if you were nearby, it would, bleh. So there are three major components that need to be removed when you're burning these sorts of things. First, there is what's called the sulfur oxides. And in a chemical formula, if you see an X, that means that could be a couple of different numbers. We use the X because it could either be SO3 or SO2. So that varies. So we just call it SOx. Sulfur, the issue with sulfur is that sulfur has a tendency of combining with water, and when it does so, it produces sulfuric acid. That's an acid that is basically being generated in the atmosphere that eventually is going to fall out in the form of precipitation, and we typically call that acid deposition. Now, if it's raining, we call it acid rain. If it's snowing, it's acid snow or acid fog. Yeah, Eric?
Would you say sulfur and water combined?
Sulfur and water combine to form sulfuric acid. Now, what is an acid anyhow? I don't know how much chemistry you guys have had, but I want to outline that for you, just in case you haven't had much. So we measure the acidity. Acidity is a measure of the amount of hydrogen ions in a solution. And the scale that we use for measuring acidity is called the pH scale. And the pH scale varies from 0 all the way up to 14, with 7 being right in the middle. And the pH scale is based upon what happens to water molecules. Water molecules water, where you actually have one oxygen and two hydrogens covalently bound to it, is in an equilibrium. That water tends to dissociate and break down into the two ions that make it up. Okay, so an ion is nothing more than a charged atom or molecule. And water breaks up into the hydrogen ion and the hydroxide ion. Hydroxide ion, hydrogen ion. So you can see there H2O. Okay, so in its broken down form, water is a hydrogen ion and a hydroxide ion. Those two charges cancel and you get a water molecule. Now, if you have a solution where you have exactly equal amounts of hydrogen and hydroxide, those will combine and you won't have any left over basically. They can all combine and nothing is left on that side of the equation, and a solution like that is said to have a pH of 7, which is exactly neutral. So at 7, the H plus is equal to the OH minus in terms of amount. Now, if you have a source of hydrogen ions that are adding extra hydrogen ions, and you have more hydrogen than hydroxide, we call a solution like that acidic. Okay, so that's an acid. Anything that has more hydrogen than hydroxide. Because once you combine all the hydrogen and the hydroxide, you have leftover hydrogens. And that charge on that hydrogen, the reason that's dangerous, it likes electrons. So it pulls electrons to it. You perceive that as a burning because you have on your skin all kinds of nice bonds between the atoms that make up your skin, and those bonds are shared electrons. So if you got hungry hydrogens around yanking those electrons off, those bonds start to break between your skin, and that's considered a burning. And if the acid is strong enough, it'll burn. Not all acids are that strong. Like acetic acid, which we think of as vinegar, you can have various concentrations of it, but in regular vinegar in your kitchen cabinet, that pH isn't too strong. Your stomach, one of the first ways you have for breaking down food is through acidity. And the lining of your stomach actually pumps out hydrogen ions. So the pH of your stomach is really low. It's like 2. So that's why if you get sick to your stomach, that's why it tastes so, one of the reasons it tastes so nasty is the acidity in that. You should recognize that this pH scale is a log scale. Which means a difference of pH between 4 and 5. 4 is 10 times more acidic than 5. And 3 is 100 more times acidic than 5. So with every number, it's not a linear scale. It's not 1, 2, 3, 4. Every change of 1 unit in the pH scale is a 10-fold change in the hydrogen ion concentration. It's like the Richter. Have you heard of the Richter scale? What's the Richter scale for?
Earthquakes.
Earthquakes. The Richter scale is a logarithmic scale too. So an earthquake of 7 is 10 times stronger than an earthquake of 6. So those numbers, and therefore an earthquake of 3 doesn't feel like much, but an earthquake of 4 is 10 times stronger. So it gets stronger really fast. If you're on this side, basically what you've got is more hydroxide ions than hydrogen ions. And we call this alkaline, or just basic. So you have acids and bases. So alkaline. Things that you're familiar with in that category are things like Clorox. Solutions tend to be really slimy. They feel slimy on the basic side of things. That has similar problems. We have leftover hydroxide ions, and all those negative charges can cause problems for bonds in your cells as well. So either one. Okay, to make a long story short, people say I get off track on things, but if I say acid and you don't know what acid means, I got to tell you about acids. So I've told you about acids now. So most rainwater is somewhere, it's not exactly neutral. There's things dissolved in it. Sometimes it's a little bit more than 7, sometimes it's a little less than 7. But at times, before people started removing SO2 and NO2, there are a lot of big power plants in the Ohio Valley and in the Tennessee Valley, and all of that exhaust would drift eastward into northern New York, northern Maine, the tops of the mountains in North Carolina, and the rain would be very, very acidic. So there were some lakes up in the mountains of New York where the pH may have been 5. Everything started dying because, you know, you start messing with pH for a fish or a little aquatic insect. That's serious stuff. And then for a long time, they're starting to come back. But who's been to Mount Mitchell? Anybody ever go to Mount Mitchell? You need to go to Mount Mitchell. It's right here in North Carolina. It's the highest point east of the Mississippi River. So it's a big mountain, and it's the largest mountain, tallest mountain in the Appalachians. The spruce trees up there were basically killed because all of that acid precipitation in the form of fog and rain and in the winter snow, it acidified the soil and the trees died. And you can still see the dead trees up there. And this was a widespread problem. And that's why through the Clean Air Act, Duke Power was required to put in these things. Yeah, Gary?
Was it turning hair green or something like that? The rain actually turning the hair? Do you remember anything like that? It wasn't effective. Was that just old?
That doesn't ring a bell. It does. There were certain green acid-loving mosses that grew on the ground that captured some of that. But I never heard.
I was hearing people.
I never heard about anybody's hair turning green.
Oh yeah.
Chlorine
I mean,
would do that.
Yeah. Now chlorine tends to be on this side, on the basic side of things.
I have to Google that.
So I don't know. That's something I'll have to look into. It could be people's hair. Maybe they just went to the hair salon. But you know, it would make sense that, you know, when people go get their hair done, that they do. I mean, the chemistry in those places. Good thing I don't have any hair, you know. But I would imagine that would be a way to change hair. You start messing with bonds, and hair can curl or hair can be straight. So that's all bonding. Mostly hydrogen bonds, which is a different kind of bond. But anyhow. Okay, so when I talk about acid rain or acid precipitation, that's what we're dealing with. So sulfur oxides is one of the things that has to be removed. Nitrous oxides is another component that has to be removed. And then the third component is fine particulate matter. And each one of those has a different part of the power plant that does that job. Okay, so let's talk about each one of those. Right here is the very first one. So fine particulate matter is removed by an electrostatic scrubber. Okay, I'll just show it to you really quick. Right here, it's this large column running next to the side of the power plant. And if you know, anytime you see terminology in this class, it's always good to break it down. So electrostatic means it's using some kind of electricity or a charge. And scrubber just means that it's taking the fly ash or the fine particulates out of the exhaust. And the way that it does that is there are plates running down this column. And those plates, the people at the plant use electricity to put a charge on those plates. And fine particulate matter has a charge to it as well. So basically all that has to happen is here's one of your plates, and here's another one, and the exhaust is passing between those plates. And if those plates have a charge, let's say a positive charge to them, then all of the, not all, but a lot of the particles, if they have a negative charge, they will stick to the plates, like a magnet. Okay, so those are charges. And then you've got this, kind of like this hammer up here that moves up and down. And when it does, it goes up and down and knocks against, you can actually hear it when you're at the power plant. You hear this constant clank, 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 and that's that hammer that's pounding on the top of those plates, and it then knocks down those particles, and you have a pile of fly ash that then gets scooped up. And where does the power plant take it? It actually takes it to a lagoon right next to the river. So they're putting all that stuff, and this has all kinds of chemicals in it: arsenic, cadmium, all sorts of fine, the coal has all sorts of little trace elements in it. It's actually, what is coal? Compressed plants. So you have all these little trace elements that were used by the plants when they were alive, not in great quantity, but they've been compacted over hundreds of millions of years. So you have a fair amount of that in there. And every now and then, one of these lagoons, like last summer, breaks, and they put it next to the river. So the Dan River, you've probably heard that in the news, that was a fly ash problem. And it polluted very large stretches of the Dan River. And people are assessing what kind of an impact that's having on the fish and on the water quality. People use, water out of rivers for all sorts of things. So there's legislation right now that's going through the North Carolina government and other places as to what should Duke Energy be doing, or any power plant, what should they be doing with this fly ash? It's a big problem. This is one of the downsides of fossil fuel combustion, is that these residues and these various forms of ashes are generally have a toxic content to them. So this is a very pertinent, you can pick up the newspaper and read about what the governor is doing about that now, and what's going to happen. Yeah.
So they couldn't reuse the fly ash for burning because this is too fine.
Yeah, you can't burn it anymore. It's basically the result of burning.
What do you think of Duke Energy's the original proposal to bury it at the airport?
Anytime you bury something, we'll talk. I don't know how much. We're not going to do a whole lot with solid waste in this class, but that's a whole other. There's a lot in the book about it. You can bury it, but burying something is only as good as the liner that you put on it. So when solid waste is put into a landfill, it didn't used to be this way. But then again, now we're talking the Clean Water Act. When it rains, that rainwater percolates through whatever you bury. Okay, and without a liner, that substance is going to get down into the groundwater, and because water moves underground, not in tubes, but percolates through the particles. So a landfill is as good as its liner, and they use a very thick plastic liner that they line a pit. So I think using it for some kind of stonework, or you'll see what they do with some of the other products. Some of it can be made into concrete or made into other substances, but that's an expense. We'll talk about SO2. SO2 is actually incorporated into drywall, and there's a whole component of the power plant that does that. Okay, I gotta keep moving. All right, here is how the NOx is removed. I don't expect you to be able to label any of this. All you need to know is you have an inlet for the exhaust and you have an outlet, and you have a chemical reaction in here. Basically, people use urea. You don't need to know the chemical formula, but it's a carbon nitrogen containing compound. And essentially, so the process, you should just sort of learn this term SCR, selective catalytic reduction. Just know it as SCR is used for NOx removal. And it's the nitrogen in the exhaust that gets reacted with the urea, and you're basically converting the the NOx compounds, nitric oxide and nitrous dioxide, and what is produced is just nitrogen gas. Nitrogen gas is no problem. 78% of the air in this room, or 78% of the molecules in the air in this room is nitrogen gas. So that is inert. It doesn't really react with anything. So that's good. These are reactive. They contribute to smog, and they can also make nitric acid, which is also contributes to acid rain. So, so basically, by reacting the exhaust flow with urea, you produce molecular nitrogen, water, and carbon dioxide, and these come out of the exhaust flow anyhow, just through combustion. Okay, so that's really kind of the main points I want you to know on that slide. You use urea, and you take the NOx out, and you make nitrogen, water, and carbon dioxide. There are different ways of doing it. This is how Marshall Steam does it. And then the SOx is actually removed using limestone. The limestone comes from West Virginia. Limestone is a lighter colored rock. It has calcium in it, and it's that calcium carbonate actually, and it's that calcium carbonate that is first, the limestone is ground down into a powder. It's mixed with water to form this slurry, and then that vaporized, it's sort of like a, you know, in the summertime you have those little nebulizers. You ever see those things? You get water droplets on you, or a little squirt bottle. Basically, it's a high energy vaporized limestone mixture. It's that fine stuff. It's blown through the exhaust, and the calcium and the carbonate react with the SOx, the sulfur oxides, and bind them. So it takes them out, and it gets deposited into this pasty stuff that's then dehydrated and turned into drywall. So here and then Duke sells that to a gypsum company that makes drywall, which is so that sulfur is actually incorporated into a product that the company sells. So that's nice. So that's SOx removal over there. And then basically what comes out the stack now is you have water and carbon dioxide. There still are some trace elements. Not everything comes out. And right now what people are talking about is what to do with the mercury. Mercury is very toxic, and there's nothing in that process that removes mercury. So there might, at some point in the future, be an added component to a power plant that takes the mercury out. When you hear people talking about clean coal is dirty. But these are all of the big efforts that the power industry has had to do in response to the regulation to make coal clean. I would call it cleaner coal. Still, you know, mining, it's a dirty job. There's no way to get the coal out of the ground that's terribly clean. But people have really been putting a lot of effort into making electricity from coal more environmentally friendly. And that's because we use so much of it, and because the nation, we have so much coal, so it's kind of hard to ignore that from an energy standpoint. We all, you know, a lot of people say, oh, we got to get cleaner, but, you know, you still want your smartphones, and we still want to use energy. So there's a little bit of a contradiction there. Most people don't want to go back to living the Amish life, which they're the ultimate environmentalists because they live on a farm and they, you know, I don't know how much they use electricity at all, but it's basically living back in the 1800s. So they're really great environmentalists, but most people don't want to live that way. So there's a little bit of a contradiction.
Oh, I drove past some Amish people all the time, Richmond.
Yeah, horse and
Just
buggy.
'cause there's a whole bunch of horse and buggy kids sitting in the back of it, and they're just staring at cars, just like.
Yeah, a lot of the kids don't
understand.
wanna, they see what's around them and they want, you know, some of them will stay with the lifestyle and others are like, shoot, man, I wanna drive a car and go to the movies and eat popcorn with hot butter on it, you know?
Country couldn't live like that way? I mean,
What's that?
country couldn't really live that way anyway. I mean, how are we gonna protect?
Yeah, how are we gonna protect ourselves? That's my point. You know, that's fine until somebody needs to go to the hospital.
Or against another threat?
Another threat, you know, you're not gonna fight with pitchforks. I think those are the two things when the rubber hits the road, defense and medical care. I think a lot of people have chosen to live a simpler life until it comes to one of those things. And then, you know, if my kid's sick, I'm taking him to the hospital to use as much plastic as you need to make my child okay. All right, so that's that.
Might as well just start now. You,
Yeah.
Nah, I got it.
we got what, like 10 minutes?
We got. You guys stretch your legs. I'll pull up the next PowerPoint.
Special event? Donald and Silva.
Tucker, hit that button for me.
Yeah, you would have.
Are all these PowerPoints